In this lesson, we're going to be talking about composite functions. We can now consider composite functions. Let's say f of x is equal to 3x and g of x is equal to x squared plus 1. We can find the composite function g of f of x, which is also written sometimes as g, the little o, f of x. Well, we always work from the inside out. So if we take an input, any input, x, it says let's apply the f of x rule because we're working from the inside out. The f of x rule says multiply your input by 3. So x is our input times 3 gives us our output, which is 3x. For g of f of x to exist, then the output or the range of my first function f of x must be part of the domain of my second, because this 3x now becomes the input of the g of x function. What does the g of x rule say to do? It says take your input and square it and then add 1. So 3x squared is 9x squared, and then add 1 gives me 9x squared plus 1. This is g of f of x. For g of f of x to exist, I just said earlier, the range of f has got to be a subset of the domain of g. For example, if I have an input x and I do the f rule to it, I'm going to get here in the orange f of x, which is the range of f. The range of f has got to fit inside of the domain of g. The domain of g has got to encompass the range of f. If that's the case, then I can apply the g rule to the output of my first function, f, to get g of f of x. So what is the domain of g of f of x? Well, if the range of f is a subset of the domain of g, then the domain of g of f of x is whatever your domain of f was, whatever you used over here for the domain of f, or your inputs of the original function. Once we establish that g of f exists, that the range of f is a subset of the domain of g, then we can substitute the values of x that belong in the domain of f directly into the expression g of f of x. For g of f to exist, that means we're going to do the function f first and use the output from f as the input of g. Then the range of f has to be a subset of the domain of g. The range of f has to be a subset of the domain of g. For f of g to exist, then we're going to do g of x first and use the output from g as the input for f. For that to exist, then the range of your g has got to be a subset of the domain of f. So range of g has to be a subset of domain of f. Here's an example with composite functions. Given that f of x equals x squared plus 1, where x is greater than or equal to 0, and g of x equals x minus 1, where x is greater than or equal to 1, determine if the functions f of g of x and g of f of x, do they exist? And if they do, find the image of x equals 3. So we have to determine if they exist or not. For the function f here, f of x, we go x 0 to infinity. So it's including 0, and it can't include infinity, so we draw a bracket like this. If I plug a 0 in for x, I get 0 squared plus 1 is 1. My lowest value for this, which I could draw a little sketch of, it's a parabola like that. So I know my lowest value is 1. So my range goes from 1 to infinity, including 1 and not including infinity. For g of x, I know that x minus 1, where x is greater than or equal to 1. So my domain is starting at 1, including 1, and going to infinity, but not including infinity. So I draw my bracket backwards like that. If I plug in a 1, 1 minus 1 is 0. So I know my lowest value for g of x is going to be 0. Because I know that this is, and I draw a quick sketch of that, it's a line like this with y-intercept of negative 1. So my lowest value, if I plug in a 1, will be 0. 0 to infinity, including the 0. First, is g of f of x, does it exist? In other words, if I do my f first, I have to determine is the range of f a subset of the domain of g. In other words, is 1, 8 a subset or equal to, that little line under there means or equal to, this? Well, yes it is. So yes, this exists. How about if I do f of g of x? That means the range of g, because I do g first, I use my output of g, my range, is that a subset of f? Well, of the domain of f, well, the range of g is 0 to infinity. Is that included or equal to this? Yes, it is. 0 to infinity is included as a subset of 0 to infinity there. So they both exist. So once we establish g of f of x exists and f of g of x exists, we can find g of f of 3 and f of g of 3. The way I did it, there's many ways to do this, or there's two ways I can think of to do this, but there may be more. I do g of f of x, which is g of f of x, which is g of, well, what is f of x? F of x is equal to x squared plus 1. So I substitute f of x for x squared plus 1. What does the g rule say? It says take your input and subtract 1 from it. Well, there's my input and I subtract 1. Plus 1 minus 1 gives me x squared. So I know g of f of x is x squared. G of f of x is x squared. So g of f of 3 is, your input is now 3, square it, you get 9. F of g of x says f of g of x. Well, what's g of x? G of x is x minus 1, so I substitute there. The f rule says square it and add 1. So I squared my input and I added 1, which gave me, I have to use FOIL, x squared minus 2x plus 1. Plus 1 gives me x squared minus 2x plus 2. Now, there's my answer. If I want to find f of g of 3, I just have to take this composite function and plug 3 in. 3 squared minus 2 times 3 plus 2 gives me 5.